This video will help you understand how to use paths to determine when a limit does not exist. I'm going to emphasize over and over again in the video that the method here will only ever work to show that a limit fails to exist. So if a limit does exist, you will not be able to use the method of paths to prove that that is the case. All right, let's think about, just our first approaches when we see a limit such as this. It never hurts to start by just checking for direct substitution. Direct substitution, I would simply plug in the values 0 for x and 0 for y, and that would give me 0 squared times 0 squared in the numerator and a whole bunch of zeros in the denominator, which effectively just turns into the indeterminate form 0 over 0. This is something that gives us no information. It does not tell us that the limit fails to exist. It doesn't tell us that it does exist. It doesn't tell us that the limit is 0. It's a dead end. Okay, it gives us no info. So we have to try some other approach. Another thing that I like to take a look at is it something that I can factor? If I can factor and cancel, that's often a nice approach. In this case, the answer is no. So I've hit two dead ends. One thing that I'm noticing now is that this is a limit where xy is approaching the origin, which a lot of times those can be nice to do, especially with these other dead ends. It can be nice to do where we say, well, maybe the limit doesn't exist. Can we check a few paths to approach 0, 0 to see whether or not this limit fails to exist? So just to kind of understand, we're going to do like a little sort of thought bubble, go back in your memory. We're going to erase this in a second. But from Calc 1, we had a method where we would look at the right-hand limit of a function. So we'd say, what if I approach from the left hand and I approach from the right, and they're not equal? In that case, we would say the limit does not exist. So let's look at a little picture of that. A nice example that often shows up is the example of a piecewise function. So let's see. As an example here, if I approach and I'm getting closer and closer to, I don't know, let's call this -2. We're looking at the limit as x approaches -2 from the left, and that limit is +3 because I'm right up here. And then let's suppose I have another limit down here. We'll call that at height -1. And the limit as x approaches -2 from the right of that function is down at -1. Since the left-hand approach and the right-hand approach to that same x value of -2 does not agree, since they are not equal, then that means the limit fails to exist. And I want to emphasize that this is actually a conclusive answer. This is not the same thing as gives no info. This is not a dead end. This is simply the answer saying, yeah, the limit doesn't exist for this right here. So this is kind of what we're going to take a look at now. However, now that we're in 3D, instead of only being able to approach from the left and right, we will actually be able to approach the point 0, 0 from all the different directions. So you sort of picture that we have a curve in space, and if we have a top-down view of that curve in space, we're trying to aim for 0, 0. And there's a lot of different ways that I could do this. One option is I could approach along the x-axis. Another option is I could approach 0, 0 and only do so from along the y-axis. But then I could also approach along the line y equals x. And for that matter, I could approach along any line like y equals 2x, or a lot of times we'll use y equals mx because that also is going to cross that 0, 0. So all of these are approaches, and I just want to point out that since there are infinitely many approaches, I cannot use this to determine that the limit does exist. The method I'm about to show will only be something where I can use to show that the limit does not exist. So let's try, we're going to do 3 different paths, and really the gist of it is that you're going to keep trying different paths until you find some different answers for the limits. So let's try approaching along the x-axis. And remember, along the x-axis, of course, y is equal to 0. So that means that this limit right here, the thing I'm really changing is the x value. The y value is staying fixed at 0 for this particular path. And when I tidy this up, that means that I have 0 over x to the 4th. Now, x to the 4th is, x is approaching 0, but it's approaching 0 along a path containing entirely non-zero numbers. So this is 0 divided by something that is non-zero, and therefore the answer is 0. We're going to see the same kind of thing as we approach along the y-axis. So that means x is 0. So now we take a look, we do really the same thing. We're going to plug in 0 for x, and that ends up giving us the limit as x, y goes to 0, 0 of 0 over 3y to the 4th. And again, this is a non-zero in the denominator, so therefore it simplifies to 0. And this is where you want to really watch out. I've only tried 2 of infinitely many possible approaches. Just because those 2 happen to both be 0 does not mean that this limit exists and equals 0. I can't ever use paths to prove that a limit exists and equals a certain value. So what I need to do is say, I've tried this one, I've tried this one. If those aren't enough to find something that's different, I'm going to try another one. For example, I might try along the line y equals x. And so what that would look like is that I would tidy up after I replace, for example, all of the y's with x's. Or I could simultaneously, equally good would be to replace all the x's with y's. So I'm going to do all the y's are replaced with x's, and now that cleans up a little bit, and I end up with x to the 4th over basically 4x to the 4th. And these now do cancel, which means that this becomes the limit as xy goes to 0, 0 of 1/4. No x's and y's left. So now we can conclude, therefore, the limit does not exist. Now, of course, the work is much more important than that final answer, right? The final answer is just the conclusion. Another thing you might see, which I really don't have to keep going, I've got my answer, but just in case you happen to see this in another example, I might give you something like this, or 2x or something, and it is important to remember as you work with that m is just a stand-in constant. So in this case, I would say I keep x as it is, I replace y inside parentheses with mx, and again, keep x as it is, replace y with mx. Notice that I'm doing that very carefully because now I'm going to apply the power to the m and the x. So the numerator becomes m squared x to the 4th. The denominator becomes x to the 4th plus 3m to the 4th x to the 4th. And I can actually pull out the x to the 4th as a common factor in the denominator, and I'm left with 1 plus 3m to the 4th. So let's think about what this gives me. M, remember, is a stand-in constant. We're assuming that it's not 0, or then we're back to one of the along the axis examples. So this is going to become just the constant, right? If regardless of what M is not going to 0. So this just becomes this, which, depending on the value of M, this is going to change. However, this right here is also going to definitely never equal 0 or an indeterminate form. So therefore, that would be enough. If I get zeros for some and any sort of non-zero, whether it's a fixed constant or something where we have a stand-in constant like M, those are enough to conclude that the limit does not exist. And once again, I want to emphasize that if you end up trying a bunch of different paths and all of them yield the same answer for the limit, you cannot conclude that the limit exists and equals that value. You're just starting to hit some dead ends in this approach, so you might want to go back and try something else.